In section 28, we're calculating the average rate of change between any 2 points on a curve or line. And to do this in the warm-up, we're reviewing a little bit about how to find slope. So we're calculating the slope between any 2 points, see if there's any kind of discernible pattern. So to calculate slope, we find the change in y, which is a +6, and the change in x, which is a +2. Change in y over change in x is 6 over 2, so it's 3. In number 2, the same thing. We're looking for that slope, change in y over change in x, as far as our coordinates go. We get a slope of 1. And number 3, calculating the slope, we get 5. So question 4 says, do the points 2, 3, 3, 4, and 4, 9 lie on the same line? And the answer is no, because if you have a linear equation, the slope has to be the same no matter what points you choose. I could have chosen 2, 3, and any other point that's on the line, and I would get the same slope. But I don't. So we know we definitely don't have a linear equation. So then what we took a look at was a formula for actually calculating average rate of change. Now, hopefully, if you look at this formula right here, the average rate of change, you'll notice that we have an output of a function minus an output of a function, divided by the input of a function minus the input of a function. The output of the function is kind of like y. The input of the function is kind of like x. So we have a change in an output over the change in the input. This right here is the slope formula. It's finding the slope between any 2 points that are on this curve G. So the question says grass clippings are placed in a bin where they decompose. The amount of grass clippings G in pounds is modeled by G of T equals 5,000 times 0.9 to the T, where T is measured in days. So right now I know for a fact that because that's 0.9, the numbers are going to get smaller and smaller as I go forward, as I increase the number of days. So on the question it says find the average rate of change on A to B. So A is the starting point of the interval. So when we find out what that A value is, we're going to plug it into here. So G of A, evaluate at A, and then A here as well. And then B is the end point of that interval, 2 in this case. So we're going to find the value at G of 2, and then divide it by 2 minus our A value. So to do this, what I did is I actually went ahead and I went to my graphing calculator, and I typed this into y equals. I typed 5,000 times 0.9 to the T. Then I used my table of values to find these different pieces. So using the formula, it says find G of 2 minus G of 0 over 2 minus 0. Because 2 is B and 0 is A. And when I do that, I'm going to go ahead and simplify that fraction down. I end up with negative 475. What that tells me is that the grass clippings are decreasing on that interval at about 475 pounds per day, because that's the measure of time in this case. On number 2, I did the same thing, but my A and B have changed, so my inputs have changed and my outputs have changed. So G of 4 is 3,280.5, and G of 1 is 4,500. Divided by 4 minus 1, which is 3. We end up getting negative 406.5. And I keep doing the same thing for all those. Now you notice that all of these different intervals produce different average rates of change. And that will happen on exponential functions. Exponential functions will have different rates of change depending on the interval. The challenging part, I think, is this last part. Using correct units, explain the meaning of it. What does it mean? So the average rate of change from 2 to 4, and let me clarify, that's day 2 to day 4. The grass clippings, we know they're decreasing or decomposing at an average rate of 384.75. Decomposing meaning we're decreasing, we're getting rid of these grass clippings. The number is the important part as well, 384.75. That tells us the average rate. But it's important to know that that doesn't mean that throughout that entire time it's decreasing at that rate. It's not like all of a sudden, once we get to time 4, the rate dramatically changes. And before times 2 is like a really different value. It's on average between those 2 points, that's what's going on. And you'll see that later when we look at the graphs will show you exactly what we're talking about with that. But then the other key component is, what is the input range? T equals 2 to T equal 4 days. We've got to have units there. Now what's cool about this guy right here, the temperature of room in degrees Fahrenheit is modeled by this function, is that's a linear function. 0.5t plus 1. We've got our slope and our y-intercept. We're still going to do the average rate of change using our slope formula. So interesting that when we do that, it appears that it doesn't make a difference what our interval is. When we calculate the average rate of change, we always get the same thing. And that's because the slope of a linear equation is consistent throughout. Notice that this 0.5 right here is the number that's in front of our variable. That is our slope that we're calculating. So using correct units, the temperature of the room is increasing. We have a positive slope at an average rate. Again, average rate, not necessarily at this very moment, of 0.5 degrees Fahrenheit per minute from, here's our units, T equals 2 to T equals 4 minutes. So those are equations and how we do that. We can also do the same thing, get down to a table here, with a table. Our process doesn't change. The only thing that we have to be careful of is what are we actually using. So H of 12 is 75, and H of 0 is 300. And I wrote them as H's. I'm sorry, those should be C's. So C of 12 is 75, and C of 0 is 300. We can calculate the average rate of change using that formula. Again, we're just calculating the slope between those 2 points. We end up getting negative 18.75. Now, based on my answers here, I'm expecting that this is an exponential function because all of the different intervals give us different average rates of change. Once again, we know it's a negative, so that means that our value is decreasing. So on the next question here, we're looking at the 12 to 24 interval. Since it's decreasing, or since it's negative, we know it's a decreasing average rate. And our units in this case is hours. And there's another one. This one happens to be linear because all the values are the same. But what I really want to take a look at are the graphs. And I want to talk about, well, yeah, let's talk about this one. So this one here, we have the floor of an elevator passes on the way down is a function of time in minutes as shown in the graph below. And find the average rate of change using this formula. So we're going to take f of 1, and if I look at f of 1, just kind of follow it up, we find out that that's 4. F of 0 is 8. So we're just using the inputs of the graph to figure out what the height of the function is. And we end up getting negative 4. Now, I could tell from the graph that this is a linear function. So realistically, I know that my answers for 2, 3, 4, 5, and 6 should all be the same thing. They should all be negative 4. Turns out that they are, just using the graph, picking out the points from the graph. So like 0.25 matches up with 7. Oh, there it is. 0.25 is 7. And 0.75 matches up with 5. Okay? Alright, so this is where average rate of change is really powerful, I think, with our exponential functions. Linear functions, we know it's the same thing throughout. But exponential functions, effectively what we have going on here are different, what are called secant segments, which you're going to learn a little bit more about in geometry. But the basic idea of this is we can take a point at 0 and a point at 2, and we can make what's called a secant line out of that and find the slope. And that's basically what we're doing. So if I take my first one here, so let's just do this. So from 0 to the value at 2, let's see where that matches up. It's at 4, okay. That's our first one. Our slope here is 3/2. But I can take the next one we've got here from 1 to 4. The value at 1 is 2, and the value at 4 is 16. So I can find a slope through those points. And you'll notice that that slope is much steeper than what we had from 0, 2. Then I can take 0, 4 and do the same type of thing. So from here to here, not quite as steep as the red line. That number is actually going to be a little bit smaller. I can do the same thing from 1 to 2. So from 1, the value at 1, to the value at 2, we got my line there. And the value at 2 to 4. So we've got, let's see, 2 is at 4, and the value at 4 is at 16. So we have all these different linear equations. What we're doing is finding the slope to create those linear equations. Now that's why with the exponential function that things get different. If we've got a very small interval towards the end of the function when it's growing, then we expect our slope to be very, very steep. If we're over in this range, we would expect our slope to be fairly shallow. If we started off at the beginning, it kind of was. 3 over 2, that's not a very steep slope. But we get towards the end here, 2 to 4, our slope is 6. That's very steep. So in the wrap-up here, the closure, using complete sentences explain what one can expect when computing the average rate of change of linear functions. We expect the average rate of change to be the same, no matter which points are selected, no matter which range of values you're using. But on question number 2, we're doing the same thing for exponential, and we expect the average rate of change to be completely different. We don't expect any two average rate of changes to be the same on the same exponential function. If we did,